We're going to be working here on the homework for 1.5, which is called continuity. And this is an interesting topic that is studied a little bit more in depth by math majors. But here we just have to have a general idea of what's going on. All right, so we're going to start out with number 2. Number 2 says, if f is continuous on the interval negative infinity to infinity, what can you say about its graph? So here we just want the basic idea. If you have a function f that is continuous on that interval, that means that you can draw this function, okay, without picking up your pencil. All right? We don't know what it's going to look like, but you can basically draw it without lifting your pencil off the piece of paper. And it'll go to the left forever and to the right forever. That's basically all we need to know for number 2. All right, so on number 3, it's a little harder because I'm not wanting to get into the habit of drawing these graphs. We're supposed to look at this and analyze it. So for 3, part A, it says, from the graph of f, state the numbers at which f is discontinuous and explain why. So when we look at this graph and we move from left to right, we want to look at anywhere we have to lift up our pencil is going to be a point that we have discontinuity. So if we look, the first place is at -4. Okay, at x equals -4, we have a discontinuity, and it's because there's a little hole there. So we call this removable. And it's removable because all we would need to do in order to fix the problem is just fill that hole in, and then it would be continuous there. Now at x equals -2, we would have to again lift up our pencil because there's a jump. Okay, so this is called a jump discontinuity. And we can't fix jumps unless we want to move the entire graph, which would not be an easy fix. This removable discontinuity is easy because you just fill in a dot and that would be it. Where else? At 2, we have another jump. X equals 2, we have another jump discontinuity. And then at 4, we have our graph dives down to negative infinity. So we call this an infinite discontinuity, because it's going to either infinity or negative infinity from the left there. And then that looks like that's it. Okay, so those are going to be the points where it's discontinuous. Now, we need to look at, for part B, each of these points and determine whether or not it's continuous from the right, the left, or neither. So let's take a look at x equals -4. Now I'll draw a little picture of what was happening here. We had this happening, right? Now, in order to be, let me draw in a different color. In order to be continuous from the left, our picture would have to look like this. This and then a solid dot. And it wouldn't matter what's going on the right side. This is called left continuous, or continuous from the left. To be continuous from the right, we would have to have a dot, solid dot, and then something coming into that dot. This would be right continuous. And so when we look at this one, this is not left continuous because that's not filled in. It's not right continuous because that's not filled in. So this one is going to be neither left nor right continuous. Also, I want to point out here, to be left continuous at -4, what we would have needed was this: the limit as x approaches -4 from the left of the function. So where you're headed in from the left would have to be equal to the function's value at 4. So this is like the solid dot right here has to be equal to what's happening as you come in from the left. And then the technical way to write this other one would be the limit as x approaches -4 from the right of the function must be equal to the function's value at -4. So the dot here has to be equal to what's happening as I come in from the right side. All right, now we don't have either one of these here. I'm just showing you this is what we would have needed in order for us to say it was either left or right continuous. All right, the next one at -2, we had that jump. So I'm going to draw that right underneath here. -2, what was happening is we were coming in like this, solid dot, and then down here it was coming out to the right. This was happening at -2. All right, so as you can see at -2, it's here, as we come in from the left, we have a solid dot there. That means I am left continuous. I'm not right continuous because where I'm headed from the right is not filled in. So, and of course it couldn't be filled in, then it wouldn't be a function. It would fail the vertical line test. I'd have 2 points at -2, so, or 2 different values of the function. So it is only left continuous here. All right, our next point of interest was at 2. And at 2, we had the opposite. We had it coming in like this, and then going out the right like that. So this one, as we come in from the left, it's not filled in, so it's not left continuous. As we come in from the right, it's filled in. This is going to be right continuous. All right, the next one we need to look at, and the last one is at 4. So at 4, we have this going on. It's diving down like this. And you can imagine there's almost like an asymptote here. And then up here, there was a dot, and it went like that. So from the left, it's obviously not left continuous because I don't go into a dot over here, so throw that out. But from the right, it does go into a dot, and it's filled in, so this is going to be right continuous. All right, and that's it for number 3. Now number 4. So for number 4, you know, I didn't even check to see how level that camera is. It's level enough. All right, number 4, same thing, they give us a picture. I think I'll draw this one. Won't take me too long. 0, -2, -4, 2, 4, 6, 8. So we're doing something like this. We've got a dot here. Circle opened up, goes over here, dot. Open circle down here, goes up through here, like that. Dot down here. Looks like we have an asymptote here. Okay, that looks like it right there. So it's asking, from the graph of this function g, state the intervals in which g is continuous. So I know there's all sorts of places where it's discontinuous. Anywhere I have these jumps or these asymptotes or these holes. Holes are the removable discontinuities. But they're asking, where is it continuous? So in what intervals can I draw it without picking up my pencil? So you can see from here to here, I can draw it without picking up my pencil. And then from here to here, and then I keep going forever. And then here this way forever. And then from here to here. So continuity-wise, we don't, okay, scratch that. Let's just start, let's just look at this. It's early, it's my first thing I'm doing this morning. Cut me some slack here. Okay, I know that I can start here at -4 because there's a dot. I can draw it until I get to -2, but I can't go to -2 because it's an open circle. And if I pick up my pencil, I'm going to have to come to here. So I can say it's continuous, all right, on the interval -4 to -2. Bracket on the -4 because I can be at -4. Parentheses on the -2 because I can never actually get to -2. So those are the x values for which it's continuous. Then, from -2 to 2, I can draw in here, but I can never be -2, I can never be +2. So I'll say unioned with -2 to +2, like that. And then, from 2 over until, well, 4, but I can never get to 4, so I can say something like this. Union 2, and then to 4, like this. And then, where else? It's continuous. Let's see, to the left of 4, I'm on this curve. I'm drawing it until I get to 6. So I can say 4 to 6, but I can never be 6, right? Because I'm going to come in here. I don't want to be 6, and then I can never get to 4. And then from 6 to 8 right here. So 6 to 8, something like that. Now, the reason why I was kind of stumbling there in a second is because it's not incorrect to make all of these open intervals. In other words, you can take the brackets off. And in class, I may just tell you to do that. And this would still be correct. And that's because it's, when we're looking at the endpoint of an interval and we're talking about continuity at that point, we can only talk about continuity here from the right. So you don't technically have to have the brackets there. But the important concept is to understand where it is that you can draw it without picking up your pencil. All right, let's look at number 5. Sketch the graph of a function f that is continuous except for the stated discontinuity. Discontinuous, but continuous from the right at 2. All right. What number is this? 5? Gonna have to read that again. Sketch the graph of a function f that is continuous except for the stated discontinuity. It's discontinuous, but continuous from the right at 2. So let's say this is 2. I need it to be discontinuous here, but continuous from the right. So continuous from the right means it's going to have to look like this. And then to make it discontinuous, I can just put a jump in there if I want. I could also have done like an asymptote, right? Something like that. But I have to have the continuity from the right, which means that as I come in from the right at 2, I should have a solid dot there. All right, that's it. I think I'll leave 11 to you. How about number 15? Explain why the function is discontinuous at the given number a. Sketch the graph of the function. So we have f of x equals 1 over x plus 2. And they're giving us the point a equals -2. So explain why the function is discontinuous. Well, if I plug in -2 here for x, I'm going to get 1 over 0. That's undefined. So since the function is undefined at -2, there's no way it can be continuous, right? What you need for continuity would be this. The limit as x approaches -2 of the function to be equal to f of -2. This is the definition of continuity at x equals -2. That's what we would need. We would need the limit as we approach -2 from both sides to be equal to the function's value at -2. If I can't even plug -2 into the function, then there's no way it can be continuous there. Now, they want us to graph this, so you're going to have to go back to your college algebra. Remember, at -2, you have something interesting happening. This is a rational function. So if you were to go and plug in some test points, you would get something like this. Go like this, die down. You would have this vertical asymptote like this. And then on this side, you would have negative like that. And then you would even have a horizontal asymptote, but that's not important right now. All right, so that's what it would look like. So it's asking here, explain why the function is discontinuous. Our explanation could be, well, we have an infinite discontinuity, or we could even say that the function is not defined at -2. Either way, it's discontinuous. Now, in number 16, what they do is they try and remedy the problem here a little bit. So let me put here what they do. They define a function. This is number 16. They define a function, and they define it piecewise. So they say, all right, let's be 1 over x plus 2 as long as if x is not -2. And then it says let it be 1 if x is equal to -2. So what happens here? Well, as long as you're not -2, you're going to draw that function, which is what we have right here. But if you are -2, they're going to define it, and they're going to define it to be 1. So you still have this vertical asymptote, but we're defining the function here to have a solid dot. So now, when you come back over here and you look at the continuity, this right side right here is actually defined, so that's not the problem, okay? This is actually 1, right? 1. Sometimes I draw my ones like this and sometimes like that. It depends on if I'm really trying to stress that it's a 1. Okay, 1. So this is not the problem for the discontinuity. That's not what's causing the discontinuity. The problem is this. This right here does not exist. This limit does not exist because when you approach -2 from the left, you go to -infinity. When you approach it from the right, you go to +infinity. So if this limit doesn't exist, then there's no way you're going to have continuity. So when you look back on the last one we did, the thing that kind of kicked us out right away was the fact that this wasn't defined. We didn't even look at this. This being undefined, we're done. But if this is defined, then we do need to look and see, is this going to match up with this? Are these going to be equal? That's the question. And if this limit doesn't exist, there's no way they can be equal. So the answer to why it's discontinuous here is because this limit doesn't exist. Now for 17, it's a different problem, so I'm going to have to, but it's piecewise. So going to have a new picture here. 1 minus x squared and 1 over x. And this is if x is less than 1. This is if x is greater than or equal to 1. All right, so let me first try and draw this. And I'll use some colors here since I've got them. I'm going to do this one in red and do this one here in blue. All right, so the red one, hopefully you recognize that. That's the same as -x squared plus 1. So -x squared is a parabola that opens down, plus 1 moves it up 1. So it would look something like this. Here's 1, go like that, and then at 1, it would be 0. You can check it, just plug 1 in there. At -1, it would also be 0. So it's going to look something like this. It's going to go down like that. This side's going to go down like this. This side's going to continue forever because that's what we're supposed to do. When x is less than 1, we're supposed to be this parabola. At 1, though, look, there's no equal sign here. I'm actually going to have to change this to an open circle like that. Okay, so that is the red part. Now the blue part, 1 over x, looks like this. Then on this side it goes like this, but we're only looking when x is bigger than or equal to 1. So notice the equal sign here. If x equals 1, it's 1 over 1, we're at 1. So 1, we go up 1, we're here. And it's defined, so I'm going to put a circle. And then as we move to the right, it's going to go down like this. All right. So let's take a look at why this thing is not continuous at the point of, it was -2. Did they want us at a equals -1, or sorry, a equals 1. That's where they want us to show it's discontinuous. So if I go to -1 or +1, here's what I would need for it to be continuous. I would need the limit as x approaches +1 to be equal to the function's value at +1. All right, well, what is the function's value at +1? Well, f of 1 is 1, so this side's 1, that's fine. And the question is, does that equal this limit? Well, since there's not a plus or minus here, we have to check both sides. So what's the limit as I approach 1 from the left? From the left, it's approaching 0, right? A height of 0. And from the right, it's approaching 1. So from the left and the right, the limits are different. And so the left side of this does not exist. And therefore, this cannot be continuous. Now, I mean, you can see it because it's a jump, it's obvious, but this is the definition and why we're running into a problem. This side is not equal to this side because that doesn't exist. Now, what are we supposed to look at? 20? Okay, all I'll say for 20, they're asking you to explain using the theorems why the function is continuous at every number its domain. Number 20 is a rational function. And if you look back on page 51, theorem 6, it says the following types of functions are continuous at every number in their domains: polynomials, rational functions, root functions, trig functions. So that's why it's continuous, because it's a rational function, except at places, except where it's undefined, right? So it's only continuous on its domain. So the only thing you need to do is figure out where that function is undefined. And that you can do by setting the denominator equal to 0, and those would be the only places you have discontinuities. So, all right, let's look at number 31. Find the numbers at which the function blah, blah, blah is discontinuous. At which of these points is f continuous? From the right, left, neither. Sketch the graph. Okay. Let me draw this, or write this function out first. F of x equals, all right, x squared, or sorry, x plus 2 if x is less than 0. 2x squared if 0 is less than or equal to x is less than or equal to 1. And 2 minus x if x is greater than 1. All right. I think I might start with a graph. All right. To the left of 0, which is this, I look like this, which is x plus 2. I'll do this one in blue. Do this one in red. And do I have a green? I do have a green. All right. I'll do this one in green. All right, blue, red, green. All right, this is just a line, right? X is just the diagonal. Move it up 2. So it would hit right here at 2. It would hit here if I was allowed to be at 0, but I'm not allowed to be at 0. I have to be to the left of 0. So I'm going to put open hole here like this, and then it should go down 1 over 1. So like that. Okay. There's x plus 2. Now the red one is defined at 0 and at 1. So that's the equal signs mean I can put dots here. At 0, we plug 0 in there, we get 0. So I have a dot there. And at 1, I plug 1 in here and I get 2. 1, 2, I'll be right here. Solid dot. And between here and here, it's a parabola. So something like that. Then the green one is again a line. I can write that as negative x plus 2. Negative x is the negative diagonal like that, but it's been moved up 2. So if I were able to draw it, I would start here. I would go down 1 over 1, down 1 over 1. I would wind up over here somewhere, right? So imagine a line that does that. But I can only be to the right of 1. So from 1 over. So if you were to draw this down, well, do it this way. If you were able to plug in 1, right? If you could, you're not supposed to. If you were able to plug in 1, you would get 2 minus 1, which would be 1. So you would be here, which makes sense. You're on that line. So I'm going to put an open circle here and then draw it like that. And I'll just continue it like that. So that is the graph of that piecewise function. Now let me get back to what they're asking here. Find the numbers of which the function blah, blah, blah is discontinuous. So anywhere I have a hole or a jump or an infinite discontinuity. So I obviously have a jump here and then another jump here. So it's discontinuous at x equals 0 and x equals 1. Then it says to talk about if it's left continuous, right continuous, or neither at each of these. So what about at 0? From the left, I am not left continuous because that dot's not filled in. But from the right at 0, I'm approaching 0 and it's filled in. So here, I am right continuous. And then at 1, notice here 1, I come in from the left, solid dot there, I am left continuous, but not right continuous, because I come in from the right and I'm here at that open circle. So that's it. All right, 33. Now 33, these are test problems right here. Maybe what I'll do, no, I'll do 33, okay. Now the reason why these are test problems is because these, you can't get away with just a graph. You've got to really think these through. You've got to use the definition of continuity to solve these problems. All right, so let me write it down first. All right, so here we go. We have a function as defined here. For what value of the constant c is the function continuous on the entire number line, negative infinity to infinity? So they want to know, well, let me say it this way. This is a parabola. If I change the value of c, it's going to change the shape of that parabola. And I'm sure I showed you this in class. If this is a cubic function. If I change the value of c here, it's going to change what this looks like. And what's happening is we have this parabola right here. Well, I'm just going to make this up, okay? This is not what it looks like. I'm just making this up. To the left of 2 on this parabola, I'm just going to assume it looks like this. And then once I get here, I have to have a hole because there's not an equal sign. And then over here, I have a cubic function. I have no idea what that looks like. But it's defined at 2, right? So I don't know, I'll put a dot here. I don't know, maybe it does something like that, whatever. What I'm trying to do is I'm trying to figure out if there's a value of c that I can put here. Maybe it's 2 and 2, or maybe it's -5 and -5. Whatever it is, that would adjust these graphs so that they actually meet up and they actually just are right on top of each other, so you could draw it without picking up your pencil. Now, to do it though, we can't look at the graph because we just don't know what it looks like. We have to go strictly to the definition of continuity. And what we need is to try and put these two together, and the only point that's interesting to us is what's happening at 2. See, because we know to the left of 2, it's this, and that's a polynomial, and that's always continuous. We know that down here to the right of 2, it's a polynomial, and it's always continuous. So we do have 2 continuous pieces. We just have to put them together so that there's not a jump. So I need f to be continuous at x equals 2. That's the big thing I need. Well, what does that mean? So I need the limit, I'm writing the definition, as x approaches 2 of the function to be equal to the function's value at 2. That's what I need. If I can make that happen, then I've got a continuous function everywhere. All right, well, let's work with this left side and right side. What is f of 2? Do we know what it is? Well, f of 2, we're going to be down here, right? Because this has the equal sign in it. So plug 2 in here and let's see what we get. 2 for x. 2 cubed, 8, minus c times 2 is minus 2c. So I have 8 minus 2c. Move this down. All right, and I think I'm going to draw that picture again real quick. Here's 2. We kind of said this was a parabola and this was cubic, and we didn't really know what it looked like. So we know that at 2, we have a dot. In fact, we know that it'll be right continuous here, because since this dot is on this piece, right, and this piece is to the right of 2, I know for sure that this polynomial will come into to that dot. So the right continuity is guaranteed because of where it was defined. What I'm interested in is the left continuity. I want this limit from the left to go down to that dot. So I'm going to change the left side of this just a little bit. I need the limit as x approaches 2 from the left of my function to be equal to this. All right, so that's very important that you understand that this takes care of the dot and the right continuity is implied. We need the left continuity. So now what I'll do is I'll say, all right, what is the limit of the function as I approach 2 from the left? So here's the function. As I approach 2 from the left, I'm up here on this thing, right? Which means I'm up here on that. I'm not looking at this anymore. So this left side is going to become the limit as x approaches 2 from the left of the function, which is this piece because I'm to the left of 2, because I'm doing the limit from the left, of cx squared plus 2x. So that's the function. That needs to equal this. And now what I can do is I can take this limit. I can let x approach 2 here and here. So what would happen if I plug in 2 here? I get 4. Plug in 2 here, I get 2 times 2 is 4. So this is going to be 4c plus 4 must equal 8 minus 2c. And notice the limit went away because I actually plugged in 2. And now I've got a linear equation. This should be pretty easy to solve. Let's get all the c's over to one side. 6c equals, bring that over here, so 4. So c should equal 4 over 6, which is equal to 2/3. All right, so let's finish this off. If I come over here and I replace c with 2/3, this c with 2/3. Then when I draw these two, this parabola should come in and meet up exactly with that cubic polynomial, and it should be nice and continuous. Now I'm debating on whether or not I should do 34. Let me talk about 34. I really want to leave that as like a challenge problem. Not that it's a bonus problem. You should be able to do it, but I think I've supplied you with enough to try it on your own. The trouble with 34 is that it's a piecewise function with 3 pieces. So you have x squared minus 4 over x minus 2. You have ax squared plus bx plus 3 and 2x minus a plus b. This is if x is less than 2. This is if 2 is less than or equal to x is less than 3. And this is if x is greater than or equal to 3. All right, so it's the same exact thing that we just did, except there's 3 pieces instead of 2 to this piecewise function. This is a rational function. You only draw it to the left of 2. This is a quadratic. You only draw it between 2 and 3. This is a line because a and b are constants. 2x, and then this could be like minus 5 or something. This is a line. You only draw it to the right of 3. So looks kind of like this. You have 2, 3. You got this weird rational function that comes in over here to 2 somewhere. We don't know where. Then between 2 and 3, it's defined at 2, so I have like a dot, and then it's a parabola, so it goes over here to 3, and then it's opened up because I'm not defined there. And then from 3 on, and because there's an equal sign here, I'm a line, so I don't know, maybe that line does something like this. Okay? Those are your 3 pieces. What we need to do is figure out what a and b are that will line all of these guys up. So it'll bring this rational function into this parabola, and that will be running into this line. The way to do this is to look at 2 different things that have to happen. You have to have continuity here, and you have to have continuity here. So, should I work it all out? I guess you could always pause the video and try it yourself, right? Okay, so I need f to be continuous at 2, and I need it to be continuous at 3. So let me start with the 2. What does it mean for it to be continuous at 2? I need the limit as x approaches 2 of the function to be equal to f of 2, right? Well, do we know what f of 2 is? Well, we go here. No, this is when you're less than 2. This is when x is greater than or equal to 2. Okay, so this is the one I'm looking at. So that was that solid dot right there. Plug in 2 for x. You get 4a. Plugging 2 in here, plus 2b, plus 3. That's what the right side will be. Question is, what's the left side? Well, if we know that the right side goes into this point, then we're concerned about left continuity here. So what I need to do is take the limit as x approaches 2 from the left of the function. So if you're coming in from the left side of 2, which function are you looking at? Which piece? Well, that would be up here, this one right here. So I'm going to squeeze this in right here. So here's where I am. The limit as x approaches 2 from the left of the top piece, x squared minus 4 over x minus 2. That needs to be equal to 4a plus 2b plus 3. All right, now let's try and figure out what this limit is right here. Well, if you try and plug 2 into this, you get 0 over 0. But last section we studied this a little bit. Looks like we might be able to factor that. Let me do that right over here on the side. If I were just doing that limit over there, limit x approaches 2 from the left, I could factor the top, x plus 2, x minus 2. On the bottom we have x minus 2, and these cancel. And so you just have x plus 2. And if I let x approach 2, 2 plus 2 is 4. So that left side is just approaching 4. So this is 4 must equal 4a plus 2b plus 3. Now we have an equation, The problem is, remember, we're trying to solve for a and b. Problem is we have one equation, we have two unknowns. That's not enough information. But I'm going to box this up, and I'm going to come back to it, because we have another equation that we're going to be able to get using the second condition, which is we need continuity at 3. So here's what I need. I'm kind of put that on the back burner, and I'm going to come over here. I'm going to change this to 3 and this to 3. Okay. And then, do we know the function's value at 3? Well, let's see, x less than 3, no. X is greater than or equal to 3, so I plug 3 in for x here. See what I would get. If I plug in 3 for x, I get 6. This side will be 6 minus a plus b must equal. And now we need this limit as x approaches 3. Well, go back to this picture here. Remember, as we were coming in from the right, that dot was there. So we know that it's the left piece that we need to kind of match up to that. So we need the limit from the left. Right? Negative sign there. Of the function to be equal to this. So if I'm coming into the left of 3, right, which of these pieces will I be on? Well, that's the middle piece, right? So this is the function that's going to replace this in the limit. And I will do that over here. Continuing that, I have limit x approaches 3 from the left of the middle function, ax squared plus bx plus 3. That must equal 6 minus a plus b. And now I will replace all my x's with 3's. So we get 3 squared 9, 9a, 3 times b plus 3b, plus 3 must equal 6 minus a plus b. And I will box that because I have another equation that has a and b in it. So I have two equations now that must be satisfied. And I have two unknowns. So let me look at this one real quick. Let me get all my a's and b's. I'm going to leave my a's and b's over here. I'm going to move the 3 over. So that equation actually looks like this. 4a plus 2b equals 1. Okay, that's this one. Now here, let me get all my a's on one side. So bring that over. I'll get 10a. Bring all my b's over. So I subtract a b. I get minus 2b. And then I'll move this 3 over, so subtract it, I go equals 3. So I should get 10a minus 2b equals 3. Two equations, two unknowns, system of equations. You can solve this using substitution or elimination. I'm going to do elimination because it's super clean, super easy right now. A reminder, quick elimination on two equations, two unknowns, is to look vertically and see if there's any way that you can get the variables to cancel. And you know, if you need to, you might have to multiply one of the equations by a number to make it happen. But I can see right away, if I add these two down, these are going to cancel. So I'm going to add these two equations straight down. I'll get 14a, these go away, equals 4. And so a equals 2/7, dividing both sides by 14. A is 2/7. Once you know what A is, you go back and you can get B. Okay, let me check something here. Yeah, that's good. We're not done. We have to go back and get B, but I'm not going to do that. I hope that helps. Definitely going to see something like that on the test.